All right, in the last video, we tried to show you how capacitors and inductors react. Um, in this video, we're going to try to quantify that reactance, okay? So we mentioned that we've known for a while of resistance being a characteristic of the path, how easy or difficult is it for current to get through. Um, and there's not really any reactance associated with resistance. It just has its characteristics as it is just a path, and it maintains those characteristics. But then when we get into things like capacitance or inductance, we find out that there's a little more to the story. So capacitance has this charging and discharging uh, action, and inductance has this bucking and boosting action. So they have what is called reactance to changing voltage. And we want to put some easier ways on paper to quantify it. We can't always be tracing it all the way back to time constants and things like that. So that's what we're going to attempt here. We're going to attempt this. Resistance is not going to change. But capacitance, we want to talk about the reactance, which we'll designate as X. And if it's capacitive reactance, sub C. And inductance, from inductors, we get reactance also, X. And if it's inductive reactance, we notate it with L. And it's worth mentioning, everything has resistance, capacitance, and inductance, even if it's just a wire. So even if we wouldn't have an actual inductor that's manufactured with a specific amount of inductance, we might still have inductance in a circuit, from just the layout of the components or something. So I do want to mention that all things have all three to some varying degree. I mean, when you make an inductor, you try to make it mostly all about inductance. And when you make a capacitor, you're attempting to make this component that has capacitance as its main feature. But inductors have resistance, and resistors have inductance, and so on. Especially wire wound resistors. Think about it. That's a coil of wire. So I want to sort of make that point that there are dedicated components that are resistors, capacitors, and inductors, and they're meant to have a specific amount of resistance, capacitance, and inductance. But don't think that that's the only place that resistance, capacitance, and inductance come from. Like we mentioned, a wire wound resistor has resistance that it's designed for, but it has a boatload of inductance because it is a coiled wire, and so on. And not to mention those coils of wire, as they lay next to each other, each coil, each each winding as it lays next to the next winding looks like two plates of a capacitor. So there's capacitance in that too. So okay, so just to let you know, that's really what takes shape for us. That it's just important that you understand that everything has some amount of resistance, capacitance, and inductance in it. And how do you then calculate the impedance of those three things as they all combine? That's what we're going to try to do. So resistance is easy. It always has been easy. It doesn't change. It just sits there. It's a characteristic of the path. The reactances, though, that come from capacitance and inductance don't just come from how much capacitance and how much inductance, but they also come from frequency. How fast is the voltage changing has a big effect on how the capacitor and the inductor react. If you remember, if voltage is changing rapidly, capacitance doesn't have as much of an impact because there's not as much time for it to charge up and discharge. Conversely, though, inductance has a big effect. If voltage is changing quickly, the magnetic field then associated with the current changes quickly and induces a high voltage of opposition. So That's what we're going to quantify for you. So let's get right on frequency, I guess, is a big thing that we have to add to this. If we want to know how all these oppositions add up for anything, whether it's just a piece of wire in computer cabling, two wires maybe, and we want to know the inductance capacitance, that becomes a big deal, or whatever we want to solve for. But frequency is a huge part of it. So let's think about this. How fast is voltage changing? Also, it's all tied up in frequency, but let's get the math worked out. So if you remember, for a sine wave, we are rotating, the sine values show up, maybe as we rotate. Let's get that sort of sketched out for us. It's this, and what we're going to do is remind ourselves that in one rotation, okay, one time around, how much we're going to try to get to a speed, an angular velocity. We're going to try to get to a speed of of how fast the voltage is changing. So let's think of it as our rate of change. So our voltage is changing, and we're going to go with arc lengths because if you remember, a radian is here, and it's the arc length that's equal to the radius. That's a radian, and there's 2 pi of those in one revolution. So one time around means that voltage will have changed by this much. 2 pi radiuses will have gone by in one cycle. And how many cycles are happening every second is this. So there are 2 pi V peaks, maybe we could call it that, because the radius for us is the peak voltage. And it's okay if you don't follow all of this. I always have a hard time sometimes conjuring all this up in my mind. But a radius for us is V peak. And how much of that, how fast is voltage changing, is simply 2 pi of those quantities every rotation, and frequency is how many rotations per second. So it's really V peaks per second. We're getting volts per second out of this, whether you catch that or not. But 2 pi f is volts per second for us. It's telling us how fast voltage is changing. It's angular velocity. It's also designated with this Greek symbol. So 2 pi f is the key to locking us in on sort of a rate of change of voltage. From that, it's not so hard then to calculate what is the opposition that comes from inductive reactance. Well, if that's how fast voltage is changing, 2 pi f, then it just comes down to how much inductance do we have, L, and we're done. So if you want to calculate inductive reactance, 2 pi f tells you how fast voltage is changing, and L tells you how strong of an inductor you have. So that's the strength of the magnetic field based on the windings, how your coil's put together. And then the 2 pi f is the speed of the changing voltage, which relates to the speed of the magnetic field. So speed of the magnetic field, strength of the magnetic field, all tell you how much buck and boost, or how much opposing voltage is generated and forward voltage push is generated. As that inductor bucks and boosts, how much opposition to current will it produce? The answer is right here. This is the inductive reactance, or the opposition coming from induction, that's generated given a certain amount of inductance. That's your coil itself that you've created, or whatever the inductance is coming from. And this is the speed of how fast the voltage is changing. Not so bad. And capacitive reactance is not so bad either. The only thing we have to remember is it's the opposite effect. So how fast is voltage changing is 2 pi f again. But if you remember for a capacitor, if voltage is changing quickly, that's a good thing as far as not generating much opposition, because it doesn't give the plates on that capacitor as much time to charge, and the charge on the plates is really the opposition to current. So if voltage is just rapidly changing back and forth, there's not as much charge time for the cap to develop an opposing charge on its plates, okay, if that makes sense. So it's inversely related to the speed of the changing voltage. So the opposition that you'll get from capacitive reactance is inversely related to speed. It's also inversely related to the size of your cap. If you remember, a larger capacitor, there's more room on the plates. So for a given amount of time, if you have a larger capacitor, it will generate, it will charge up slower, so there'll be less opposing voltage that's coming from the charge on the plates. So all that to say, the capacitance, the bigger it is, the less opposition you'll get to your current. So there it is. Just again, opposites in every way, inductors and capacitors. And here mathematically we can see that their reactance to changing voltage, this is opposite. The faster the voltage is changing, and the larger the inductor, the more opposition or the more inductive reactance that you'll get. And for a capacitor, it's the opposite. The faster the voltage is changing and the larger the cap, the less opposition you'll get, the less reactance. So there's your mathematic formulas. If we want to, we can tell ourselves again that resistance was not complicated. It's just as it always was. And by the way, the units for all of these, when you calculate reactance, it's ohms, it's ohms, it's ohms. Okay. And Z, which will be the combination of all three, R, XL, and XC, all combined for a total opposition to current, which is known as impedance and abbreviated Z. That's also in ohms. Okay. Let's see, what else did I want to say? There was a thought. I lost it. But let's jot this down for you. Z is going to be a total combination of XL and XC. Where do I want to put that? Over here maybe. That's Z, and that's also in ohms. We mentioned before, let's put it here, I guess. Unfortunately, it's not as easy as just saying, let's add them up, because, but it is in ohms, by the way. Well, because the reactance of capacitance and inductance don't happen at the same time, at the same instant in time. So we'll develop that, I guess, next. I wish I could think of that previous thought. Let's see. Yeah, not gonna get it. Okay. Let's talk about how we can combine, these oppositions to current into a total impedance. Probably the easiest way to see it is to use current as our reference waveform. So let's do that. Let's get a waveform going here. Now, and we're going to be working with all of this in a sine wave context. So voltage is going to be rolling up and down. It's not going to be like the square wave that we use to illustrate, you know, inductance and capacitance initially. So that's going to be a little different, but let's get our sine wave in here. Okay. And let's talk about how things look. Well, first of all, if that's current, then I can tell you what the voltage or what the impedance will look like across a resistor. It's going to be right in step with that. As current rises and falls, resistance follows the voltage of a resistor. It'll be right with that. So that's why we can use the voltage across a resistor to always know what's happening as far as current in the circuit. Now, with that, let's look at capacitive reactance and inductive reactance to show you how they're not all happening at the same time, okay? That'll be the game here. Well, one way to look at this is the whole time the current is flowing in this direction, if you have some capacitance, it'll be charging up the whole way through here. Does that make sense? Current is flowing. So all that time, a capacitor will be developing voltage on its plates, charging up. Its peak voltage is going to be over here then, at the end of all the forward current that's happening, is where you would find your maximum voltage of across your capacitor, which is its maximum impedance. It's going to be its maximum. So its reactance is going to happen over here. So this is how the voltage of the capacitor would look. And also it's showing us that the opposition to current is maximum here, right here. For an inductor, a couple ways you can look at it. One way is right here, looking here, the speed of the rate of change, the slope of this current as it changes is also an indicator of how fast the magnetic field is moving through the inductor, and its speed, its slope is maximum right here. So the inductor is going to have its maximum voltage sitting here. Okay, so we've got this just to look at. That would be the voltage of the inductor. So the inductor is going to be opposing maximum here, and look, the cap is actually 180 degrees from the inductor, and like we said, that also again shows us that they're opposites in every way. Yeah, I wish I could think of that initial thought that was going to help lead us into all this. I'm just trying to show you that the difference in timing that happens with the reactances of inductance and capacitance. You know, I guess another way to say it is when the inductor is bucking, you know, the capacitor, the inductor might be bucking current, and at that time the capacitor is actually accepting charge rather easily. So they can cancel each other out. If you have an equal amount of inductive reactance and capacitive reactance, they'll just compensate for each other and take each other completely out of the mix. The inductor, when it's blocking or bucking, the capacitor is like, that's okay, I got plenty of room on my plates at the moment, so it's charging, so current will flow. And then the other way around, I guess, when the inductor's boosting, I guess, trying to think if I'm saying this right. Um, that might be when the capacitor is charging. Yeah, yeah. The capacitor will be charging and accept the boost from the inductor, so it doesn't have any net effect. And when the inductor is blocking with a buck, the capacitor is discharging and offering up its coulombs, even though coulombs from the source can't get through. Okay, we don't have to map it all out to that level. I'm just trying to get across the fact, helping you believe that bucking, boosting, charging, discharging don't happen at the same time, and so the reactances, which is where the impedance comes from, don't happen at the same point in time. And in fact, the inductor and capacitors reactance and impedance happen at 180 degrees apart from each other, and they happen 90 degrees apart from any resistance. That's sort of just the path itself, its characteristics, its conductive properties. They happen 90 degrees from that. And maybe if we just look at this, I think there was probably some other thoughts I could have done to sort of make that a smoother transition for you, but it's okay. If you believe it, great, and we could always explore it some more later. I want to show you that yes, the cap and the inductor are 180 apart. They're 90 apart from any resistive opposition to current. Some people know this little acronym. I don't know, it sort of sticks in their head. You'll hear this sometimes. I mean, Eli the Iceman, it doesn't really make sense, but it sticks in your head, I guess. E for voltage. For an inductor, L, you get voltage first and then current. And that's always the case. And we can think all the way back to our square wave experiments. Yeah, it blocks with a back EMF, you get voltage, and then current follows after that as the magnetic field relaxes or slows down. So voltage and then current. And for a capacitor, you get current first because it's charging. It'll accept lots of current, and then voltage follows. As the cap charges up, current decreases, and voltage increases. So E for voltage. But that, people might throw that at you, Eli the Iceman. That's another way people try to remember this whole relationship. What I want you to catch is that things aren't happening all synchronously at the same time. And quite the opposites for caps and inductors. So they're at 180 to each other, caps and inductors, and they're 90 degrees difference to what's going on in the resistor, through the resistor. So this is, I don't know if I've done a great job of leading you through this picture, but the new reality that you need to understand is in an AC circuit where voltage is changing in time, it's quite the show going on in the circuit, in that it's not one waveform happening. Your voltage across your resistor in your circuit, your resistances, will be one waveform, and then inductive voltage across any inductance is going to be leading that, and voltage for capacitance is going to be lagging that. Overall, the total circuit voltage will be yet another waveform. So when you actually look at what's happening in a circuit that has resistance, capacitance, and inductance, and all do to some degree, and then when you hit it with a sine wave, you have maybe 4 sine waves to look at: a total circuit voltage, a total circuit current. This is a simple series circuit I'm talking about. But you would have maybe the circuit voltage, the circuit current shared by all, and then you would have maybe the voltage waveform across an inductor or a capacitor. They would be doing their own thing. So yeah, so it's it's quite a lot going on. 4 different waveforms. They're not all in phase. They're not all happening in sync with each other, is the point. Okay. Yeah. We can try to get back to, and we'll see where I want to leave this video. At least we've shown you, I hope, how to get the reactances. Let's just show you how to combine them. If the total impedance then is not simply the addition of them because they're not happening at the same time, let's see what it is. So to do it, you have to do what's called geometric addition. Inductive reactance, we can represent that, you know, with an amount. The length of this vector, I'm trying to draw straight up and down, represents how much inductive reactance. Remember, that comes from 2 pi FL. So there's going to be a certain amount of inductive reactance. There's going to be a certain amount of capacitive reactance, okay? How much? I'll just put a little bit in there, but the length of that is how much? So that's 1 over 2 pi FC. And I might have some resistance, okay? So how much resistance do I have? I'll just put in that much. But this is how you have to do it, because they don't happen at the same time. And like we said, the XLs, it's 90 degrees and 90 degrees and 180 with each other. So you're going to add them up like this. So just for kicks, let's say I have, you would do the calculation, 2 pi FL. This would be a certain amount. Let's see what it looks like. Let's say this is 20 ohms of inductive reactance. And let's say capacitive reactance, 10 ohms of capacitive reactance. And I would have gotten that by calculating 1 over 2 pi FC. What for capacitive reactance? You know, what's the size capacitor? What's the frequency that I'm using in the circuit? 2 pi times that, 1 over that, and it's an actual amount in ohms of opposition that's coming from capacitance, and an actual amount of opposition that's coming from inductance based on the frequency. Because remember, it's not based on the inductor or the capacitor alone. It's also what frequency are you applying. Let's say that's what I calculated. And then let's say I have 30 ohms of resistance just from the, you know, how conductive the path is itself. So let's just put that out there. So the total impedance then, we said, is not just simply adding those up. So it's not 60 ohms. It's not 10 plus 20 plus 30, because they don't happen at the same time. Well, what is it then? So Z, we're gonna look and see, okay, whatever inductive reactance you have, and whatever capacitive reactance you have, first thing you got to do is see that they cancel each other out. They're an opposite. They're 180 degrees from each other. So like I mentioned to you, it is possible for them to totally cancel each other out. If they're exactly the same, they actually help out and make up for each other's faults, right? But look, I've got 20 ohms of inductive and 10 ohms of capacitance. So overall, it's going to be inductive, but it's going to be, just by subtracting, I would have 10 ohms net reactance. Now, the thing is, the reactance that I'm left with is still at 90 degrees to the resistance. So we can use the Pythagorean theorem. After you've done that, let's look at what we're left with. We're left with 10 ohms, right, of net reactance, and it's inductive. And then, let's see, we still have our 30 ohms of resistance. And do you see, I'll just put make it a little more obvious. There's a right triangle here that I can solve. This length here is my total impedance. So what we want to do is take whatever reactance, after you've combined the inductive and capacitive reactance to a net reactance, that's what we have here. You square that, because it's going to be a squared plus b squared equals c squared, right? Because it's a right triangle. So a squared is the net reactance. I'm sorry, that would be b squared, wouldn't it? But so b squared plus a squared, which is our resistance, whatever resistance equals c squared, which is z, but I'm going to square root both sides, okay? And there's your answer. So it's just the Pythagorean theorem that we're using to geometrically add our different oppositions to current that don't happen at the exact same point in time. So that's why we have to do it this way. But these are easy enough. They just wipe each other out. So you just subtract them, but then you have a net reactance that you have to use the Pythagorean theorem to geometrically add to whatever resistance you have. And that's it. I mean, we could get our total impedance here. Let's see. So Z then, what is it? It's 100, right? 10 squared plus, yeah, am I doing this right? 10 ohms net, square that, 100. 30 ohms, sounds like 900. Oh, I got lucky here, didn't I? And we're going to square root that. So Z, it's 1,000. Square root of 1,000. Let's see here. Let's see what that. 31.6. Okay. Looks like that's the answer. You know, and I guess it's reasonable. We can double check it if I did my math right or not. It looks like the hypotenuse here isn't that much longer, right, than this adjacent side, right? Because, I mean, this isn't that long. So 30 ohms of resistance, 10 ohms of capacitive reactance, 20 ohms of inductive reactance. Overall, the total opposition to current in this circuit would be 31.6 ohms of total impedance. And that's what you do Ohm's law with. This is how you would know the circuit current right here. Well, it's an introduction, isn't it? I guess. This might seem like a lot. Hopefully, let's see the highlights. What I wanted you to get out of this presentation is 2 pi FL tells us how much inductive reactance you're going to get, and 1 over 2 pi FC. Of course, they came from the size of the amount of inductance you have, and not to forget the frequency, because that the amount of, it's easy for me anyway. I sometimes think it's easy for me to make the mistake of thinking, oh, it's based on my inductance. I mean that this is the opposition to the inductive, opposition comes from the inductance. It's like, but don't forget frequency is equally a huge player in there, as equally important. Okay, capacitive. How much capacitance do you have? That doesn't determine this. It's half of what determines it, but frequency is the other half. You can have a large capacitor or a small capacitor in it, but frequency is the determining. And here, if you have a large inductor, you might be tempted to think, well, I'm going to have a lot of opposition. Then it's like, well, no, it depends on the frequency you're using. If you're using a low frequency, you're not going to have much opposition, no matter what size inductor you have. Okay. So that's a big deal, and those are the new things to add to what we already were using, was resistance. And then we have to find a way to combine all three, and this is how we do that. The total opposition to current, then, known as Z, impedance, comes from combining geometrically inductive reactance, capacitive reactance, and resistance into a total impedance. Frequency is buried in here. It depends on frequency, but total impedance. And that's what you can do Ohm's law with. And maybe just in closing, we can mention, that in previous days of the DC course, what did we have? We had V, I, and R. And we did Ohm's law with that. You can still use Ohm's law, but now we're a little wiser and we know to do V, I, and Z. Z is the whole story. Z is what you can do Ohm's law with, and it takes into account any capacitive and inductive reactance. We didn't need it in the DC course because the voltage wasn't changing in time, so frequency was 0. But now we need it. And you can calculate Z from inductance, capacitance, and frequency. You can also know from Ohm's law that whatever voltage you have and whatever current's flowing, that is your impedance. So don't forget that you can use that. Ohm's law still works. If there's a certain amount of voltage and a certain amount of current, that's not meaningless. I mean, that's absolutely as useful as it always was. So that's another one to remember. Z is that as well. Okay. Well, yeah. I feel like I missed a point that I wanted to make, but at least we got these things introduced, and we can keep developing it from here. We'll probably end the video here. I don't know if there's I don't know that there's more that I wanted to do. We're not done with concepts. With this presentation, I think you can see how to combine the oppositions to current that we've come to understand. The only other big thing left to do, but I do it in a separate video, is to calculate these phase angles that occur, because with the charging, discharging, and the bucking and boosting comes opposition to current. That's true, and we figured that out, and we figured how to add it all up. But also with the charging, discharging, bucking, boosting, it knocks things out of phase. So voltage and current aren't necessarily in phase. And then it's nice to know, well, where are they? How out of phase are they? In other words, you can calculate the total circuit current if you know the total impedance, but it's also nice to be able to calculate the phase angle between voltage and current. So that we'll do that in another session, and it's going to be just more trig right off of here. We can get it. We can get it from this from right triangle stuff. But yeah, well, that's the other piece of the puzzle. It's one thing to calculate total circuit current. That's great and that's important. But then the other piece, the other big piece of the puzzle is once you've calculated circuit current, the question then is, what's the phase angle between circuit voltage and circuit current? We'll do that in another video or just in a lecture. We'll figure it out. Okay, I wish I could think. It's still bugging me where I wanted to go with some of this up here initially. We'll leave it. Maybe I'll patch that up later. So, all right.